Welcome to this lecture where we're going to talk about the types pair, set, and map from the C++ standard library. These are important classes, so we want to introduce them here. You'll be using them in Project 2, let's talk about them. The pair class is a really very useful class. I find it extremely useful, and all it does is it allows you to easily join together any two types. Okay, so you can say a pair of type A and type B. So you could have a pair of int and string like I've written here. So I can declare pair int string, that's the type, and I could call the variable that I'm allocating P, and I could provide initial values 256, and data structures are awesome. So this would create an object called P that has two elements, and the first one is called first, and the second one is called second, and I can directly assign to them if they're not const, right? I could say p.first equals 128, and I could say p.second equals so are algorithms. Now, I want to point out one interesting and useful function is called make_pair, which you'll notice up here I had to specify the two types, int and string. Make pair infers the types, which is convenient and useful. And I could say p equals make pair 64 pairs are sweet, right? So this is a very useful class for just gluing together any two objects. So if you ever have pairs of things that you need to put together, the pair type is there to do it for you. And other interesting fact about the pair that I didn't say here is that if you compare two pairs, so if I have pair X and pair Y, and I say, is X less than Y, the way this works, it'll do this for you. It'll compare X dot first with Y dot first, and if X dot first is less than Y dot first, then this returns true. And if X dot first is greater than Y dot first, then this returns false. But if they're equal, then it resorts to comparing the second values. So it compares first values first, and then it resolves ties with second values. And that actually ends up being pretty useful when you want to sort the second things by the first quantity or by the first type. Okay, so pairs are neat. They're pretty small, pretty easy to use. Now, more complicated types are the set and map classes. The set class and the map class are both templated classes, containers, and we'll go through them. They're very similar in a lot of ways, so we'll go through them from simpler to more complex. The set, which takes a type K, we'll call it K here, K for key. The set is like a mathematical set. And if you know what a mathematical set is, then that's great. But if you don't know what a mathematical set is, then you should look that up. You know, a mathematical set we usually notate with curly braces is like, maybe 1, 3, 5, right? This is a set that contains the elements 1, 3, and 5. A mathematical set can contain any types. The only requirement about a mathematical set is that all the objects in there are unique. And that's the important thing about a STL set as well. They're all unique. Now, mathematical sets can contain any type. So I could have a set that contains integers and strings and houses and balls and phones and whatever. But an STL set, rather, all the types, all the elements must be of the same type, which we specify with this template, okay? So we call these things keys, and they must all be unique. The C++ set adds these two restrictions. They must all be the same type. That's what I just said. And in addition, mathematical sets are not kept in order, but STL sets are kept in order. They're kept in order under the hood using what's known as a red-black tree, which is a type of balanced binary search tree. And we'll talk about those later in the semester. Now, in order to keep them in order, in order to keep the elements that it stores in order, the set elements of the set, the k's that we're storing in here, must be comparable by operator less than. Okay, so in order to store 1, 3, and 5, I have to know which is the least and which is the greatest. And in order to do that, we use operator less than for those integers. So any type that you store in a set must be comparable by operator less than so that it can store them in this ordered binary search tree. So that's why in Project 2, we have to support operator less than for the location class. Now, a map is exactly like a set, but with one extra thing. You'll notice that map has two templated types here, K and V, K for key, V for value. It has a value with it, which is associated with each key. And you can think of this as sometimes what's called an associative array. In other words, it supports the operator bracket lookup with a key. Okay, and I'll show you an example of that in a minute if that's not clear. But we can use the syntax of what looks like an array lookup, even though it's not actually an array. That's why we call it an associative array. And within the map, inside the map, there are pairs everywhere. Every entry in the map is a pair of key and value. And you see this whenever you sort of delve into the internals of the map, especially if you iterate over all the elements of a map. So to be clear here, one thing I should be clear about is that a set stores a bunch of unique keys. A map also stores a bunch of unique keys, but the values need not be unique. So the keys in the map are unique, but the values are not necessarily unique. Okay? Now, some important methods for these two data structures are the insert method, which allow us to put something in, obviously. The find method, and for both the set and the map, we find based on the key only. And the find method, if we try to look something up, it returns an iterator. And that iterator either points to the thing that we were looking for, where the key is equal, or if the item was not found in the set or the map, it returns the end iterator. The end iterator, as we have talked about, is it's one past the last valid iteration point in the collection. So this is what's returned if the key that we're looking for is not in the set or the map. Okay, so enough sort of high-level stuff. Let's look at some details. Here's an example of a program that would run if you put some scaffolding around it that uses a set. Okay, so we declare a set of integers. Integers, of course, are comparable by less than, so we can make a set of them. And I declare an integer I, and I say just read this while loop. Will just read integers as long as we can, okay, until the standard input stream closes. So we just read an integer, and as soon as we read that integer, we try to look it up in the set. And if this is true, then what's true about this? Well, if find returns the end iterator, we know that the set S did not locate the thing it was looking for, in this case, I. Okay, so in other words, here, this branch of the if statement means we did not find I in the set, and so the program says, interesting. In other words, that's new information, and so the set is going to insert I and remember it for later. Okay, but if the find operation did not return the end iterator, what does that mean? Well, that means that the set found I, and it's just going to print out, you're repeating yourself. Now notice I don't insert it a second time. Why not? Because it's already in there. What would happen if I inserted it a second time? Would I have two of them? No, because a set keeps only unique items. So if you insert something a second time or a third time, you don't get multiple items because a set only keeps unique items. Okay, so this sort of ties together all of the different really important parts of a set, the find, the end, and the insert methods. Okay, and of course there are other methods, but not that we really need here. Here's a similar program, but with a map. Suppose we have an integer I, a string S, and a map which goes from string to int. So this is the key is a string, and this is the value is an integer. So we have M is a map which stores a bunch of unique strings, each of which has an associated value, which does not need to be unique. And notice that it's going to read in a string, look up that string. We only look up by key, not value. And if it's not found, then the program says, what does that mean? What does that string that you just typed in mean? And if at that point, it will read an integer, and then it will enter that pair into the map. Now, notice there's no pair written here. This is the associative array syntax that I was mentioning before. We say m sub s, remember the string is the key, equals I. So we're actually creating the entry here and then assigning the value I. Another way we could have done this is we could have explicitly used a pair and we could have said m.insert make pair s comma I, which would have done the same thing if it was not already in the map. Okay, all of this happens if we had not seen that string before. And otherwise, we're just print out what is the value associated with that string. So this is going to look up in the map what that string maps to, and then print out that value, that integer, not the string, just the integer. Okay, so you might, why would this be useful? Well, this program might be useful for if you wanted to type in the word FOUR and understand, and then the program says, what does that mean? And then you type in the number 4, and then the next time you type in FOUR, it would print out 4, okay? And you could type in, you know, TWO, and it would say, what does that mean? And you could type in the number 2, and it would say, keep that. Now, there's nothing limiting you to redefining these as you wish, but you could imagine that this would be a way of translating between English words for numbers and actual numbers, okay? Now, a few comments on the lookup speed of sets and maps. Both sets and maps are, they implement the find algorithm in order log n time. And that's because the underlying red-black tree keeps things in order and keeps things balanced. And if you compare this with, if we were to try to keep a bunch of unique items in a array or a list or a vector, it would require looking for things that could be anywhere in the list or the vector or the array in order n time if we didn't keep them in order. So log n is significantly faster than order n. And that's one of the reasons that we want to use the set and the map for fast lookup. However, that hides a little bit of complexity because the set and the map are more complicated than these simpler data structures up here. An array is much simpler than a set or a map. And so if you have a really small collection, very few locations, very few items that you want to store, these simple ones, the array, the list, the vector, are probably going to be faster than a set or a map. However, if you had a very large collection, I'm talking in the thousands to millions to billions, then this log n is going to be much, much faster than order n. So there's a trade-off here of complexity, complex code in the set and the map, but you get a speed up that kicks in for large values of n, okay? So that's it on pairs, sets, and maps. And if you do some more reading in the project guidelines and some of the documents I've provided on the web, I think you'll find more details that will be helpful here.